Welcome protein coders. Let's build some coding muscles. Today we're gonna see Kruskals algorithm. But before that, let's revise about the minimum spanning tree first. We saw that earlier that a spanning tree is a graph in which all nodes are connected and no cycles present. Okay, and what is a minimum spanning tree? In the spanning tree only when we have the weighted edges, we will choose that spanning tree which has the sum of the total edge weights as minimum. And for that, we saw an algorithm called Prim's algorithm. Let's revise what Prim says. In Prim's algorithm, we choose a starting node, let's say A, okay, and from A, what we will do is we will select nodes which has shortest edge weight from the visited nodes. Okay, nodes which are part of MST. Those are called visitor nodes. Okay, so let's start from A. You see we have 3 as the minimum edge, so we will move to B. And now A and B are the part of MST. From A and B we'll choose the minimum edge. So we have 4 edges. Okay, so let's choose one first. A to D, mark D is part of edge, then A to C, and then if you see we have from C to E as minimum edge, which is 2. Now again if we choose the minimum edge, we will get the edge C to D. But if you look carefully, if we choose edge C to D, then it will form a cycle ACD, and we don't want cycle in a graph. Similarly with the case of B to E edge. Okay, so we will reject those edges, and again we will continue. We'll move from C to F and then from F to G. So that's what Prim's algorithm is. We have to just keep in mind that we'll choose the shortest edge weight node from the visited nodes. Okay, now let's see the Kruskals algorithm. What Kruskal says is choose globally minimum edge weight nodes and combine them. Okay, now let's start. So minimum we have C to E, which is 2, so we will combine them, and then A to B, which is 3, combine them. Then again we have 3/4, right? So let's combine A to C. But if we join B to E, then it will form a cycle, and as you all know, in minimum spanning tree we don't want cycles. Okay, now let's continue again from A to D, then C to F, because C to D will form a cycle, so we will move from C to F and we will combine them, and finally F to G. Okay, so that is what Kruskal says, and we don't want cycle, right? So what we can do here, when we reach at combining B to E, we got an edge from B to E, we can just use DFS or BFS from B or from E to know whether I can reach from B to E or not, right? But if you see the time complexity for this, it will be order of V square or V into E, right? Because I'm going to perform DFS and BFS for all the edges, right? So to check for the cycle, I need something better, and that better algorithm we studied previously is DSU. With the help of DSU, we will detect the cycles, whether we can form a cycle or not with a given edge. Okay, so now let's see the Kruskals in brief. What we want to perform in Kruskals, we will first form an edge vector which will store pair of weight and U and V. Okay, then we will sort the edges to get the minimum edge every time, and before combining we will check using the find operation of DSU whether they are in same component or not, or else we will combine them, and during combining we can also add the edge weight, accumulate the edge weight as the minimum spanning tree weight. Okay, now let's see the code part. First we will make our edge vector, right? Pair of integer and comma pair of comment. Now let's get the nodes and the edge weight, and the first component should be, when we are pushing in edge, the first component should be weight and then U comma V. So that's it. Now let's sort our edge vector. Now let's create our DSU object. Let's name it DS, and a MST weight vector which will count the total weight, and edge used. We will see the use of edges used later on. So let's iterate in our edge vector. We'll get the weight, U and V. Simple. Now we will check, before combining we will check if find of ds dot find of u is not equals to ds dot find of v, then only we will proceed. What we will do is, first we will combine them. Okay, we will get them into the same set, then we will increase the MST weight, and at the end we will increase the edges used, that we use this edge. Now here comes the optimization. If the edges used is equals to v minus 1, that means we formed our MST, we no need to check further, so we will break from this loop. At the end we will return the MST weight. So that's it guys, this is the code of the Kruskals. That simple it is. Let's revise what we have studied. In Kruskals, what we are doing is, we are first forming the edge vector, then we are sorting the edges, right? And before combining we are checking using find operation, and then doing the union and accumulating the MST weight. Now we saw in the code for the same, right? For every edge we will get weight u and v. We will check first whether this edge will create a cycle or not. If not, then we will count the edge weight and do the union. In the end we will return MST weight. Now few more things I want to discuss with you guys. The time complexity of Prim is e log v, and whereas Kruskal says e log e. So because it is log e, right, because of sorting, and e log v because of min heap. So here in Kruskals you see it's dependent on log e. Okay, so if the edges are too much, so it will be not preferable. So Kruskals is always preferable in sparse graph, while Prims is always in dense graphs. Implementation wise, you can see Prims we will use when we are given adjacency list, and Kruskals when edge list is given. Prims can always be performed in a connected graph. This is the criteria for Prims. But in Kruskals, if the graph is not connected, right, it can handle the disk connected graphs also. But what we will get is spanning forest. What is spanning forest? It's a collection of spanning trees. Okay, this is the very interesting point which Kruskals give us. So keep this in mind. And if you see the example, Prims in dense graphs, you can say computer networks, very dense computer networks, and in Kruskals a sparse graph like electric wiring or something. Okay, so that's all from my side guys. Hope you enjoyed this, you learned something new. If you have any questions and queries, please mention them into the comment box. You will find the problem and the solution link into the description box. If you don't understand, don't like, don't subscribe, but if you do, please show some support. Keep smiling, keep practicing. Thank you.